Okay, so now when you look at this summation over here, I mean this is what we want to prove, right? So let's work towards it. Now one kind of basic hint is that whatever is stated in the prerequisites or the assumptions for the theorem, you will find that all of them get used. Without it, I mean it's not possible for you to prove it. So what are the things that we have in mind? What are the nuts and bolts that we have? Descent direction, that means cosine theta greater than 0, that is one thing that we will have to keep in mind. Wolf conditions, what are the two Wolf conditions? Sufficient decrease and curvature conditions, these. Then f is bounded from below. These are the 4 ingredients of the recipe that we will have to kind of use. Okay. So notice that what I want to prove has a summation of norm of gradient, right. Now has everyone heard of telescoping a series? So when I telescope a series, that is when I can add lot of terms, right. So your hint is when you see a summation happening in over here, that there is going to be some kind of a series which I telescope and I am going to get a summation, that is going to give me some hint. But if you did not know that, that is okay. Let us start with the curvature condition.
This convergence condition is true for any algorithm with a valid descent direction and with alpha k satisfying.
Yes, which is why it is very powerful, not curvature condition. So what is the curvature condition telling us? Again, it is better if you recall the geometric flavor of it rather than the exact thing. What was it saying? That the slope of the linear approximation is smaller than the slope at alpha equal to 0, right. And the way we wrote it, what was the slope at alpha? Minus grad fk plus 1 transpose pk. Why minus? Because otherwise slope was a negative number, I made it positive. I said this should be less than or equal to the slope at 0, right. So the slope at 0 was, and we relaxed it a little bit, right, C2. This is how we wrote it. Now let us get rid of these minus signs. So what will I have? And let us open it up. So f of xk plus alpha k pk transpose pk, there is a minus sign I am multiplying on both sides. So this becomes greater than equal to C2 and f of xk transpose pk. Which curvature condition? Was this the strong Wolf condition or the regular Wolf condition? In the strong Wolf condition we put a mod, but there is no mod here. So this is the weaker one, okay, but it is still good enough. Okay. Now what I would do is let us subtract grad fk transpose pk from both sides, okay. So this is grad fk plus 1 minus grad fk transpose pk. What will I get? This is going to be C2 minus 1 grad fk transpose pk. Okay. Okay. Now let us see. We also want to use this Lipschitz condition. This Lipschitz condition is telling us what? That if I see norm of gradient differences, I can replace it by L times norm of x minus y, okay. That is something that we want, that we can potentially use, okay. Okay, let us see if I can retrace the steps. Okay. Now let's just talk about Lipschitz over here. Okay, talk about. And to talk about Lipschitz, I have to talk about the difference of two gradients, right? So that I see there are two gradient expressions being subtracted over here, right? So let's write those down. So I have grad of fk plus 1 minus grad of fk, okay, transpose with pk, okay. Can I relate this to the norms of both of these vectors, an inequality? Inner product of A and B, can I relate it to the norm of A multiplied by norm of B? Less than or equal to, right? This is less than or equal to norm of grad fk plus 1 minus grad fk multiplied by norm of pk. Why? Cos is between, cos has magnitude between minus 1 and 1, right? So this, the term on the right is always going to be greater, right? I got this difference of gradients over here, right? Immediately can I apply Lipschitz? Lipschitz is saying that this norm of grad fk plus 1 minus grad fk should be what? Less than equal to L times exactly sk plus 1 xk plus 1 minus xk pk. Is there something nice I can say about xk plus 1 minus xk? Alpha k pk, right? So this is equal to L into alpha k is a positive number, therefore I have norm pk squared, right? So let's call this 1, let's call this 2. Okay. So can I combine, should I, okay, that's right here. Combine 1 and 2. Can I combine 1 and 2? This term over here is greater than something, but this same term over here is less than something. So can I combine these two inequalities? Yeah. So what am I going to get? I am going to get that L times alpha k times norm of pk squared is what? Greater than or equal to C2 minus 1 grad fk transpose pk. Right. So this is actually giving us a very interesting inequality on alpha k. Alpha k, we thought we could take any really small number, but what this is saying is alpha k is actually like this. So we have used curvature condition, we have used the Lipschitz condition. Okay, what have we not used? Bounded from below we have not used, and sufficient decrease we have not used. So of the Wolff conditions we have used only one condition, which is curvature condition. What is left to use is the sufficient decrease. Now sufficient decrease simply says that the function value at k plus 1 should be what? Should lie below the linear approximation of the function at k. So this is what it would be, fk plus, what is the linear approximation? Alpha grad fk transpose pk, and when I throw in the relaxation, what will happen? C1, right? So always remember these conditions just by their English statement. It's you won't go off, right? Function value below the linear approximation. Curvature is slope at that point is less than the slope at the starting point, right? That's what gets us this. Now actually this is the guy where we can use the idea of telescoping a series. You see that, because I see fk plus 1 and fk on either side. Now if I write this out from f1, f0, f2, f1 like this over here, what will happen? I can cancel off these guys. That's going to be the intuition over here, and the term that is left, the second term on the right hand side, is what is going to give me the summation. But let's get there. I have an inequality here on alpha k, right? Can I substitute this in here? Will the inequality still hold? I want to use, this is condition 3. Can I substitute it in here? Yes, right. So, this is going to be fk plus c1 c2 minus 1 by L grad fk transpose pk whole squared divided by norm of pk squared. Okay. Alpha is greater than this, yeah. So, this whole expression is even greater.
Alpha is greater than that term, so this whole expression would be like less than this term.
No, why?
This inequality would reverse the.
So, here is my alpha k, and if I substitute this guy over here, I mean this will continue to hold this way, right?
Yes, but this implies alpha k is less than that term.
No. What is the smallest value alpha can take? This guy, right? This is the smallest value, and alpha can take any other value. Does it? Anyone else have a problem here? Did we make a mistake in the third inequality then? It looks correct to me. Right, when I combine 1 and 2, this is exactly what I got, and I got this. Actually, one quick question, this term on the right hand side of 3, is it a positive number or a negative number? C2 is less than 1, that's okay, that's not enough. Right, the overall term is positive because it is a descent direction. So, pk transpose grad fk is actually a negative number, right. So, this is telling us alpha k is above some positive number, right. So, is this fine? The direction of the inequality is fine over here, okay. One common thing that is done is that this C2, as we just observed, that C2 is actually less than 1, right. So, what people will do is we will write this as like this. We just bunch up all of those constants into one number c. C is equal to C1 1 minus C2 divided by L, okay. We are almost there. What else can you see? This term over here, does it remind you of something? Cosine squared theta k, that is it, into the C. Okay, right. So, if I open up this grad fk transpose pk, it is norm of grad f, norm of pk cos squared theta, right. So, norm of pk is going to get cancelled. I am going to be left with, this is fk minus c. Can you tell me what is left? Will I have a cosine squared? I am going to have a cosine squared theta k. Is there anything else that is left? Something is going to be left. What is that something? Grad fk squared, right. And so, let us rewrite this over here. This is fk plus 1 is this. So, we are almost home. So, you notice that this sufficient decrease condition was very useful because it is relating fk plus 1 on one side and fk on one side. What is left for us to do? Just collapse this pack of cards, right. So, if I collapse this pack of cards, oops, f0, f1, f1, f2 like this, everything is going to get cancelled off and I sum it up. When I do this, what will I, so let us write telescoping. Let us say I telescope it up to k terms. So, is there anything left to cancel fk plus 1? No, that is the final term. what other term will not get cancelled? F0, right? And F0 is going to appear on the other side. So, this is going to be less than equal to F0 minus this guy, the summation is left. So, I am going to have C summation j equal to 0 to k cosine squared theta j we have yet to use the fact that this function is bounded from below, right? Bounded from below would come in now, right? That fk plus 1 should not become minus infinity or something like that. It is going to be some finite number, right? So, if I subtract f0 from it, I will still be left with some finite number. So, I can since f is bounded from below, I will take this on the other side, I am going to get, and c is a positive constant. So, I can knock it off. Which is actually our zoutendijk's, oops, sorry, that is not what I want to say, right. This is going to be fk, f0 minus fk plus 1, which is some finite number. We do not know whether, I mean, it is a finite number and it is a positive number. Okay. So, this is, so we can write over here QED over here, this is the condition that we wanted. So, many students, when they see this proof for the first time, they think, I mean, even I got the feeling the first time when I saw this, that this is just a rabbit pulled out of the hat, how will we ever know how to do this? But as you read more and more proofs in this area, you find out there are just a few tricks that people use. Those few tricks are telescoping series, replacing inner products by norms by inequality. Once I have norm of grad f x minus grad f y, Lipschitz helps me to get to norm of x minus y. So, there are a few tricks over here, there are not too many tricks, and when you read all the proofs, okay, there are 4-5 tricks which people use. When I see a summation in a result, I should immediately think of telescoping a series. To telescope a series, I need the function values which I got from sufficient decrease condition. Okay. So, these are just some common tricks over here, and from here the corollary, as I mentioned, that is what? That as limit as k tends to infinity, cos squared theta k grad f k tends to 0, right. And then the other thing we said is that p k is a descent direction, which implies that cos of theta k cannot be equal to 0, right, which says that right. So, this is the, now that we already spoke about the intuition before we started the proof, you are not lost by all the details. Now, you already know that once you reached this zoutendijk's condition, you knew immediately what to follow next, that okay, there are so many terms that are being added and the sum is still finite. Therefore, let us, in the limit as k tends to infinity, what I am adding must be very, very small. What is left for me to parse out? Cos theta k has to be a strictly positive number, that is gone. What is left? Norm of grad f k. Norm of grad f k tends to 0 is what I was looking for, because that establishes that it is a stationary point, right. So, what is this saying? That if my cost function look like this, right, this is guaranteeing that if I start over here, I am going to end up, oops, I am going to end up here, because this is the point at which grad f k is 0. This does not tell me at all that I will land up here. Similarly, if I start, let us put a cross over here, if I start from here, I will land up over here, I will not land up over here, right. That is what is the implication of this. So it's guaranteeing that I will arrive at a local, can I say minima? Yeah, we can say minima. Although if I just say grad fk equal to 0, it need not be a minima, it can be a maxima. But what is helping us? That we are choosing descent directions, right? So it's inconceivable that I end up at a maxima by choosing descent directions, right? So that's about as good as you could do with gradient descent in a general real life non-convex non-linear function. This is the best that you could do, okay? And what is helping us is calculus. Calculus is helping us to bound all of this, right? If I didn't have this Lipschitz continuity condition on the gradient, I wouldn't be able to get this, right? So it's a strong condition to apply. There may be some real life functions where you cannot do it. And so this proof assumed a few things, right? What did it assume? Bounded from below anyway is a common sense condition, but it assumed, for example, Wolff conditions, and which is good because I didn't demand exact line search. That would be a strict condition, right? So this is fairly general as far as proof goes, okay? So did we, for example, ever assume that pk was equal to minus grad fk in this proof? Nowhere did we assume, right? So what is this telling us? Pick any descent direction. It's not, this proof is not restricted to gradient descent. You can come up with your own funky algorithm that always goes at 30 degrees with the negative gradient. No one's stopping you from doing that. You will still reach the result. No one's stopping you from doing that, right? So that's why this is a very powerful proof to work with. Okay, so I think what, as far as content goes, we'll pause over here for today. So I mean, we started with this backtracking line search review and various other kind of ways of doing it, fitting polynomials, quadratics. Then we looked at line search, how does the trajectory look like, and we derived some simple relations, for example, the steps being perpendicular to each other, which did, I mean, use simple calculus. Then we said, let's try to find out, does this method converge, and we said yes, and we proved this under this zoutendijk condition, which used all of the ingredients of the theorem to land us up at norm of the gradient tends to 0, which is what we wanted to prove. Okay. So we are not going to, I'm not going to do a detailed proof of convergence for the other methods, okay, because they get more and more involved as we go, but I wanted to give you one proof because one proof everyone should know. It's not very difficult, okay. So any questions? Something not clear? Okay, so the second method over here, yeah, the 3 points were, I started over here at alpha, this is my alpha, this is my phi of alpha, this is 0, and pick some point alpha, right? And I am saying I know the value of the function at 0, I know the value of the gradient at 0, and I pick some other point over here. You can either say either phi dash alpha or phi alpha, you take a pick. But basically 3 pieces of data allows me to fit a quadratic in this range, for example. Whatever, it could be anything. Once I know that, I can analytically solve for it, find the minima and move to that. If it turns out that my function is actually quadratic, then I have solved it.